friends, in this course we will cover important topics of statistical inference. This is a second major course in the subject of probability and statistics. We have one basic course on probability theory, where we talk about the concepts of probability and distributions, and in this course we broadly discuss the methods of statistics as applied to day to day problems. We will be mainly covering in this course point estimation, in the point estimation we will cover the fundamental concepts such as unbiasedness, consistency, efficiency, and then we will discuss the methods of finding out the estimators such as method of moments, maximum likelihood estimator, estimators. Then we will discuss the uniformly minimum variance unbiased estimation, the method of lower bounds for determining these, method of lower bounds, and another concept is that of through sufficiency and completeness. We will cover another major area in inference, that is testing of hypothesis. We will discuss how to find out various kind of tests, what are the types of errors, the fundamental concepts of testing of hypothesis, and determination of the tests. So, in the determination of tests we will discuss most powerful, uniformly most powerful, tests, and then a related concept, that is of likelihood ratio tests. We will also discuss the problem of interval estimation. In this we will discuss the methods of finding out confidence intervals for usual one sample and two sample normal distribution problems. The important textbooks that can be used for this course are an introduction to probability and statistics by V.K. Rohatgi and A.K. M.D. E. Saleh. Another important book is Statistical Inference by G. Casella and R. L. Berger. A first course on parametric inference by B. K. Kale. Modern mathematical statistics by E. J. Dudwigs and S. N. Mishra. Introduction to the theory of statistics by A. M. Mood, F. A. Grable and D.C. Boyce. Those who are interested to get advanced knowledge on statistical inference may further look at the books Theory of Point Estimation by E. L. Lehman and G. Casella, and Testing Statistical Hypothesis by E. L. Lehman and Romano. These books cover almost all the topics that will be taught in this particular course that I am going to start today. So, let me firstly introduce what is the problem of statistical inference and why should we study it. So, let me talk about the introduction and motivation of statistical inference. We notice that many phenomena in various sciences, they are governed by laws which are not deterministic in nature. So, we can call them stochastic or probabilistic in nature. For example, if you look at the amount of rainfall in various parts of the country during a monsoon season, then it is not sure that how much rainfall is going to be there in the next year, how much it will differ from the previous year, whether over the entire geographical region in which we are interested in, whether there will be a uniform distribution of the rainfall, or in some portions there will be tremendous rainfall and in some other places there will be a condition of drought. No matter what physical theory we develop or what atmospheric scientists are able to develop the theory, they can never be sure of the exact amount, the timing of the rainfall, etcetera, in different geographical regions. So, we can say that these are governed by probabilistic laws. Similarly, suppose I consider the time taken by patients to get cured by a disease while undergoing a particular treatment. So, quite often we observe there are patients who are given a certain treatment for a certain disease. We observe that a patient A gets cured within 2 days, whereas patient B takes 10 days to get cured, and there may be a patient say C who may not get cured by that particular medicine, and he may have to be given another type of medicine. So, the effect of the medicine on different patients are quite subjective in nature, they depend upon various conditions. Therefore, these are stochastic in nature. Similar examples are the number of persons in a service queue at a ticket counter or at a petrol pump. So, for example, if we go to a railway counter at a given time of a day, we find that at that time there are large number of people standing in a queue. So, for the next time of the when we need the booking, we go to the counter at another time thinking that at this time there will be less number of people, and we find that that is not true. At another time when we go, we find that the number of customers or the number of persons standing in the queue is much less. So, the number of persons, this the need of the persons to book in the different trains, etcetera, is also not deterministic in nature. The number of children in each family. So, these kind of problems, when we look at these kind of phenomena, they are all stochastic in nature. So, these are nicely modeled using the probability distributions. So, the application of probability models to these kinds of experiments, this has led to the development of methods which are commonly called the methods of statistical inference. Some typical problems where one uses statistical methods to arrive at a solution are deciding on the basis of sample inspection of lots in a manufacturing process whether the quality of product is satisfactory. So, you consider a factory where certain kind of nuts and bolts are being produced. Now, we are the factory owner or the manager of the production, he is interested to know the quality of the production. If the quality is all right, it will be sent to the market at a appropriate price. On the other hand, if the quality of the product is not good, then it will not be sold at high price. On the other hand, it may even be returned. So, the quality of the production is very important. So, now how do he goes about it? He looks at the batches of the product, for example, maybe in 1,000 or in 100, and he inspects randomly say 10 out of each lot of 100, and he makes a decision based on that whether there are more defectives or less number of defectives. For example, he observes that every lot of 10, it does not produce more than one defective product, then he may conclude that the production of the bolts is satisfactory or up to the given marks. Another problem of inference could be that on the basis of a random sample of persons who are in certain employment, we want to estimate the average salary or wages in a country. So, this kind of situation or this kind of inference is important for determining economic policies of the government. It is important for the say consumer goods producing companies. They, if they find that the average salaries are high or on the higher side in particular place, then they may like to sell the appropriate items to that zone, because they may get more customers. On the other hand, if they find that the average salaries are much lower, then high cost goods may not be able to be sold in the market at those places. Another problem could be that, for example, nowadays there is a lot of talk about climate change, global warming, etc. So, the scientists are interested in knowing how much increase of the temperature will be there in the global climate during next say 10 years or next 5 years, on the basis of the data which is available to us from the past 50 years or from past 100 years. So, on the basis of this, we will be able to estimate how much will be the average temperatures in different places or overall global temperature. This is going to be useful to determine the policies of the various organizations, various governments, that what should they do to reduce the global warming or the effect of the global warming. Another typical example of statistical inference is deciding on the basis of clinical trials whether or not a new drug is to be approved for human use for a particular disease. So, there is a disease for which certain drug may be or may not be available. Now, doctors or the persons who are involved in the development of the medicines, they come up with certain substance, certain biochemical substance, which they find to be effective against the disease causing bacteria or virus. Now, how do they go about it? So, they design an experiment where a certain medicine is produced using certain amounts of that clinical and that biochemical substance, and now once it is decided or the amount is decided or amount is determined that this is going to be actually useful in curing this disease, then it is the question of introducing in the market. Now, the medicine can be introduced in the market only if it is found that after taking this medicine there are no side effects, as well as it has a high efficacy as compared to the previously used medicine, or if there was no medicine, then it should be better than the control. That means, even if the medicines are not taken, if some people are getting cured, then this medicine should be better than that. So, it is the job of the statistician, on the basis of a random sample, he will decide how to take a decision in arriving at a conclusion whether this new medicine is going to be effective or not. Estimating infant mortality rate in a state or a country based on a random sample from that region. So, people talk about the development. So, we say that a country has a high GDP or gross domestic product, and therefore, the country is on the path of a growth. But whether from the human development index point of view, whether there is an overall development. So, we look at other parameters such as infant mortality rate, the literacy levels and other factors. So, we want to notice find out what is the infant mortality rate in that country. If the infant mortality rate, despite having high GDP or high average salaries, even if it is high, then that means it relates to certain other kind of traditions, certain other kind of conditions which may exist there, which are not, which despite high GDP growth are not going to improve the infant mortality rate, etc. So, a social scientist and the planners of the country are interested in knowing the what is the estimation or what is the estimate of the infant mortality rate. A frequently encountered problem is that there are various kind of guns which can be used in the by the army. Now, army wants to buy new guns to replenish its stock of the arms. So, now various arms manufacturers, they give the samples from their factories, and then the field trials of those guns are conducted. So, the job of the statistician is to determine that which is the best gun among this, which is the second best, etc., in terms of its performance. Performance could be in terms of accuracy, that or the range that the gun can cover in hitting the its targets, its robustness in the sense that depending upon the different terrain, whether it is hilly region or whether it is a plain region or whether it is a desert region, whether the gun can be equally effective in different temperatures, in different timings of the day, etc., and also the longevity of the gun, that is also important. So, the job of the one needs statistical methods to determine which is the best, which is the second best, and so on. That means, we have to order them in some preference. So, these kind of problems are usually formulated using a mathematical model, or you can say a statistical model. So, on the hand, you can say the field person gives some data to the statistician. So, the data is in the form of certain numerical values or some observed values. So, the statistician treats these values as the values of a random variable x. So, we use a notation, say capital X, which denotes the random variable whose observed values are given to the statistician by the user, by the end user. So, they call it the values as x 1, x 2 and x n. As an example, we looked at the problems So, we are looking at say sample inspection of lots. In the example of sample inspection of lots, what will be x 1, x 2, x n. So, suppose 10 lots are inspected of say 10 products each. That means, each lot of the bolts contains 10 bolts, and we are looking at in terms of say the diameter of the top or the length of the bolt, etc., anything which which is the quality control terminology used for describing the goodness of that product. So, we may use that. Now, the data could be in the form of say 0, 1, 2, 1, 1, 0, 0, 1, 0, 0. So, these are the 10 values. That means, the lot number 1, it had no defective, lot number 1 had 1 defective, lot number 2 had 2 defective, lot number 4 had 1 defective, lot number 5 had 1 defective, lot number 6 and 7 had no defective, lot number 8 had 1 defective, lot number 9 and 10 had again no defective bolts according to the criteria that has been fixed by the quality control manager for that particular product. So, for statisticians these values will represent the values of x 1, x 2, x 3 up to x 10. So, the random variable x denotes here the number of defectives in a lot of 10. So, in a lot of 10 there are x number of defectives. In fact, in this particular case one can find out the corresponding probability distribution. For example, if I say that there are x number of defectives in a lot of 10. So, one may use a binomial model or one may use a hypergeometric model depending upon the conditions that have been imposed on this kind of situation. Suppose there is a constant probability p of being defective, then this probability will be 10 C x p to the power x 1 minus p to the power 10 minus x for x is equal to 0, 1 to 10. That means, you may have a binomial model to describe the distribution of x. Let us consider another problem. Suppose we are looking at the random sample of working persons and we are looking at estimating average monthly salary in the country. So, in this particular case, if we are looking at estimation of monthly salary of the persons, say employed persons. So, the values here would be calculated as x 1, x 2, say x 20. Suppose 20 persons have been considered here, then the values could be in terms of rupees, say. So, you may have, say, for a person it could be 1200 rupees, for another person it could be maybe 20,000 rupees, for third person it could be say 1700 rupees, for one person it could be 800 rupees, etcetera. So, here x 1, x 2, x 20 denote these values, and now we may use this data to have a model. So, for example, the model may be given by certain distributions, say f, it could be normal distribution, it could be gamma distribution, etcetera, depending upon the actual values that have been obtained there. So, the probability distribution of x is modeled using standard techniques of fitting of the distribution, and therefore, we can say that x has a distribution say f x theta, which of course, may be discrete or it could be continuous or it could be mixed, and theta denotes some characteristic of the population which could be scalar or the vector. Here x itself can be scalar or a vector depending upon the type of the things we are having. For example, the situations that have been described now, here in all these cases x is a discrete random variable. However, there may be some other situations. For example, I am looking at x as the observations are taken on a person regarding his health. He goes to a medical practitioner and he wants to have an estimate of his average health. So, the values that x may take here may consist of certain components, say x 1 which may relate to his age, x 2 may relate to his weight, that is his body weight, x 3 may denote his blood pressure. Now, blood pressure may consist of two values. So, you have two values here. So, you may consider them as x 3 and x 4. Then you may have his sugar level and so on, say his pulse level. In this case, x is a random vector. Similarly, the parameter of the distribution f for the x. So, the parameter theta itself may be a vector or it may be a scalar. In the case of monthly salary, if we are having a distribution such as a normal distribution, then the normal distribution is characterized by two parameters, say mu and sigma square. In this case, my theta is consisting of two parts. If we are considering say the number of persons arriving in a queue in a given time period, then we may model it by using say a Poisson distribution, which is having a parameter lambda, which is the rate of arrival here. So, for different problems, we will use different probability models to describe the setup. So, we are having x1, x2, xn as the random sample, which we treat as the observed values of a random variable x, and x will is assumed to have a known distribution f x theta, and therefore, the distribution consists of certain parameter which is called characteristic or parameter of the distribution. So, the distribution of x is completely specified when the value of theta is known. Now, in standard situations, although we may arrive or determine at a form of f, but in most of the practical situations it is not possible to fix the value of theta in advance. We may find out the distribution is normal like, or it may be Poisson. Poisson model is more appropriate to describe the number of arrivals during a time period, the number of failures. Similarly, in some situations we may arrive at a conclusion that binomial model is more useful or gamma distribution is more useful, but the appropriate parameters of that distribution one may not know in advance. So, the distribution is completely specified if the parameter is known, but in most of the practical situations it will not be known. So, the definition of the statistical inference or the problem of statistical inference is to determine on the basis of the given data that what would be the value of this unknown parameter. So, it is not necessarily that we just tell the value. So, the general problem of statistical inference is to make suitable statements or the assertions about the unknown parameter of the population. Here we can break this up into two broad areas. One is that some feature of the population in which an experimenter or inquirer is interested. So, let us say g theta, this may be completely unknown, and the experimenter would like to make a guess or estimate about this feature on the basis of a random sample from this population. So, this is called the problem of estimation. So, here he may come up with a single value for as an estimate. So, for example, when I say average salaries, and he may come up with a figure say 2200 rupees per month. If we give a single value or a unique value for the unknown parameter of the population, this is called point estimation, because we are giving a single value, that is a point. On the other hand, we may specify a range. For example, when we talk about the expected temperature in the coming year, then we may say that the expected average temperature during the month of June is likely to be between 42 to 44 degree Celsius in a particular region of the country. So, here we are not telling a single value like saying average value is 43 degree Celsius, rather we are giving a range. Now, this range has to be qualified using certain probability statement. This is called the problem of interval estimation, and this is another part of statistical inference. So, in estimation we may specify a single value or we may specify a range of values. This is called the problem of estimation. So, this is one major area of statistical inference. The second major area or broad categorization of statistical inferential problems is that we may have some information regarding the unknown feature of the population, which is available to the experimenter. Now, the experimenter would like to check whether the information is appropriate or it can be sustained in the light of the random sample which is drawn from the population. So, this is called the problem of testing of hypothesis. So, let us go back to the example of a new medicine getting developed. So, a biochemist he has derived a new substance and tested in the laboratory that it is quite effective against a disease causing bacteria. Now, the assumption is that the average effectiveness of the medicine by which is prepared using this new substance will be more than the corresponding value, or you can say. So, now when you are testing this effectiveness, you have to identify in what terms you are measuring the effectiveness. Is it the proportion of the patients getting treated successfully, or is it the length of the treatment, or is it the survival rate, etcetera. Suppose we fix here our measurement of effectiveness of a medicine by the proportion of the patients which get successfully treated. So, let us call it P. So, now that means suppose we give the medicine is given or the treatment is given to say 100 patients, out of that how many get cured. So, we look at the proportion. Suppose this proportion is P for the new drug. Now, there is an existing drug which had 60% cure rate, that means 0.6 is the proportion which was curable using the previous drug. So, now in order to have, or you can say in order to introduce this new medicine in the market, we would like to check whether this P, the proportion of the patients getting cured using the new medicine, is greater than 0.6 or not. This is called the problem of testing of hypothesis. So, this is the outcome of this test will be determined by the statistician using an appropriate statistical method. So, in this particular case it will be an appropriate test. So, based on a random sample of certain patients who are given the medicine, one will need to check this thing. There is another distinction which I would like to make at this point. There are situations where due to not having enough data or due to volatile nature of the data, it is not possible to model the data according to a known distributional form, such as normal distribution or a gamma distribution or an exponential distribution, because many times the data is huge and it may be having lot of variations. Therefore, appropriate known probability models are not suitable to fit that distribution. So, such situations are considered by statisticians over the years, and they have developed methods for estimation and testing, etcetera. These are called popularly as non-parametric methods or parameter free methods or the distribution free methods, and this comes under the topic non-parametric inference. In this particular course, we will be spending almost all our time in discussing parametric inference. So, by parametric inference then we refer to the problem when the appropriate probability distribution has been specified and the problem is now reduced to making inferences about the parameter or a function of the parameter in the form of estimation, which could be point estimation or interval estimation, or testing of hypothesis. So, these two fundamental aspects, that is estimation and testing of hypothesis, they are used in almost every area of statistical methodology. For example, we consider predicting a future response. I mentioned the problem of predicting the temperature for the forthcoming year. We would like to predict the average food production in the next year. We would like to predict the average industrial growth in the next year. So, these are the problems where the past data and certain other variables are used to predict the future thing. So, here this type of inferential problem is treated under the topic of time series analysis. Similarly, there are areas where we determine the relationship among the variables. For example, the effect of providing say irrigation, say modern equipment, good quality seed, and say good quality of insecticides or pesticides etcetera to the farmers, and we look at the response in terms of the increased food production or increased yield of that particular crop. So, here the response variable is y, that is the yield, and the variables which are determining this, they are called regressor variables here x1, x2 etcetera, that could be the amount of irrigation facility, the amount of modern equipment, the modern fertilizers and other kind of things. This topic is generally covered under the subject regression analysis. Designing of the experiments, which is again used in the various industrial, agricultural, medical experiments, ranking and ordering of populations etcetera. So, all of these advanced areas of statistical inference, they use these fundamental aspects, that is the estimation and the testing. Now, at this stage I will introduce certain terminology and their exact meanings in the context of statistical inference. The first important terminology is the term population, which I have been using till now from the beginning of this lecture. So, a population in a layman terminology refers to a collection of individuals, could be human beings or it could be cattle or it could be insects. So, generally a population refers to living beings, that means the entities themselves. For example, a population of a country, population of say sheep in a population of a sheep in a state, population of say rats. So, we say that there are problems because the population of rats is increasing rapidly in a particular city or in a particular state. However, a statistical population is not the collection of individuals or the units, it is the collection of the measurements, or you can say aggregate of numerical or qualitative records of measurements on certain characteristics of interest. So, we looked at various problems just a while ago. So, we considered one problem of say estimating the average salary of the employees. So, here what would be the population? The population is the records against the salaries of the employees. So, suppose we are looking at an industrial organization. So, we may look at that all the employees which are employed in that particular industrial organization, and so suppose there are 10,000 employees there and we have them marked according to their employee code or any other identification code. Then the values corresponding to their salaries. So, for example, I am identifying the employees as 1, 2, 3 and so on up to 10,000. Now, the salary of the employee number 1, that is x 1, the salary corresponding to the employee number 2, that will be called x 2 and so on. So, x 10,000. So, in this particular case the population of interest is these 10,000 entries. If we are looking at the weight at birth of the children in a certain geographical region, then for all the children which are born during a particular period in a particular geographical region. So, we look at the value of the weights taken in say pounds or in kilograms or in grams corresponding to all the children born. So, here the population is that aggregate. If we are looking at the incidences of deaths due to accidents on the road in a city on each day of the year, then each day we record the number of accidents taking place and then the corresponding deaths in those accidents. So, the population here is the number of the deaths on each day. Responses to a new legislation to control the freedom of speech in a country. So, a new legislation is placed in the parliament, or it is proposed by say by the cabinet, then say the opinion polls are taken whether it is a popular measure or not. So, here the responses by the persons will be in the form of, say, they are whether they favor it or no, not. So, it could be answers could be in the form of yes or no. So, the answers which are now here in the form of qualitative answer, that means, it is in the form of attribute, that is also consisting creating, or you can say this collection is my population in this particular problem. On the basis of this, we may have to make the inference whether it is going to be a popular measure or not. Once we have identified a population of our interest, the next key the key term is parameter. I have been using this term parameter repeatedly beforehand, but however, what is the proper meaning of the parameter? So, the specific characteristics of the population, such as average, for example, it could be mean, median, mode, arithmetic mean, harmonic mean, etcetera, or a characteristic of this use for which determines the variability, such as standard deviation, range. Suppose it is determining the whether the population is symmetric or not, maximum value, minimum value, etcetera. So, whatever the characteristics in which the experimenter is interested in. So, the characteristics which are related to the population, they are called the parameters. So, usually the parametric inference assumes a distribution f x theta. So, here theta is the parameter which characterizes the population. So, the popular examples like we say Poisson lambda distribution. So, lambda is the parameter here. If I say normal mu sigma square distribution. So, the distributional model is normal and it is characterized by the parameters mu and sigma square, etcetera. Here mu and sigma square are the mean and variance respectively. In the Poisson distribution, lambda itself is the mean as well as the variance of the distribution. A statistic. So, this is the next terminology. A statistic is a function of the sample observations. So, from the population, the statistician has at his disposal a random sample. On the basis of this, which he will make the appropriate inferences. So, the sample is termed as observations x 1, x 2, x n. So, any function of these observations, let us call it a t x, where x is denoting the sample x 1, x 2, x n, this is called a statistic. So, in a point estimation problem, we usually identify a statistic, let us call it say d x. This is called an estimator of the parametric function g theta. So, for example, in the suppose we have a Poisson model and we are having the rate lambda and we are interested to estimate say 1 by lambda. So, my parametric function is 1 by lambda. So, now it is a moot question whether we can find out an estimate for 1 by lambda, or we may be interested to estimate say lambda to the power 3, we may be interested to estimate in a normal distribution say mu, we may be interested to estimate sigma square, we may be interested to estimate sigma, and we may be interested to estimate mu plus say p sigma, which is denoting a quantile. So, depending upon the interest of the inquirer or the experimenter, one needs to determine which parameter is to be estimated or inference on which parameter is to be made, and the corresponding statistic has to be framed from the sample which will be useful for the purpose. So, for example, in the normal distribution one may use sample mean to estimate mu, one may use sample variance say 1 by n sigma x I minus x bar whole square to estimate sigma square, or one may use 1 by n sigma x I minus x bar whole square to estimate sigma square. In a interval estimation problem, in place of one statistic, say in this point estimation we are proposing 1, that is dx, but in interval estimation we need 2, that is end points of the interval where my parameter of interest is supposed to lie. So, we need to specify say d 1 x and d 2 x, so that we can make a probability statement regarding the parametric function g theta lying in the interval d 1 to d 2. In testing of hypothesis, we use a statistic, let us call it say phi x, for taking a decision to accept or reject a given hypothesis. In this case, phi x is termed as the test function or test statistic. So, these are the basic terminologies which are to be used in statistical inference. We have a population. So, that is the first thing, that where we are interested, what is our interest to study in the given setup. So, we identify the population, we draw a random sample from the given population. Now, drawing of a random sample itself is a matter of full investigation. It comes under the topic of methods of sample surveys or methods sampling techniques, and it is another aspect of the statistical methodology, where we discuss various methods of taking of random sample. In this particular case, we assume that a random sample is already available to us. Now, our job is to use this random sample to draw appropriate inferences in the form of point estimation, interval estimation or testing of hypothesis to inform the end user about the appropriate conclusion of the about the population parameters. So, parameters are the characteristic of the population in which we are interested in. The decision is based on the random sample, and for that purpose we use a function which is called a statistic. So, in the point estimation problem we will create a point estimator using the statistic. In an interval estimator we will create an interval which is in the form of two statistics giving a range. In a testing of hypothesis problem we will specify a test function or a test statistic using that random sample. At this point, let me briefly give example here. So, let us consider the problem of say average monthly salary of the employees in an organization. Now, let us assume that the model for this is described by say Pareto distribution. So, a Pareto distribution may be having a continuous distribution, the density function is of a given form say alpha beta to the power alpha divided by theta to the power say alpha plus 1 sorry x to the power alpha plus 1, where x is greater than beta. So, in this particular case we have considered a 2 parameter model, where the parameters are alpha and beta, both are of course positive. Now, here we may be interested in the average monthly salary. So, average monthly salary denotes expectation of x, that means from this distribution what is the value of the expectation of x, which can be of course easily calculated. So, this value turns out to be alpha beta to the power alpha x to the power minus alpha plus 1 divided by minus alpha plus 1 from beta to infinity. So, alpha beta to the power alpha, and then when we substitute the value at infinity this will vanish, and at beta this will become. So, we will get beta to the power alpha minus 1. So, the value turns out to be alpha by alpha minus 1 beta, where of course, alpha has to be greater than 1, otherwise this expression will not be valid. So, now in this particular problem we want to estimate this parametric function. So, this is my g theta. Here theta is a vector parameter consisting of two components alpha beta. So, now to estimate this, now there may be different procedures. As a layman, one may say that take the random sample x 1, x 2, x n and we may use x bar, that is the sample mean, to estimate this. So, this could be one method, and of course, depending upon the situation one may develop the different methods, as we will be seeing during the course of during this course. On the other hand, one may have to do some sort of testing here. One, we may like to check whether the average income levels are low or high. So, for low or high we may identify a control. We may say that if the average monthly income is more than say 5,000 rupees, then we may say that they are well off or well paid, and in that case we may devise a test statistic based on x 1, x 2, x n to take a decision whether this hypothesis is tenable or not. That means, we want to have a hypothesis whether the average monthly salaries is more than 5,000 or not. I will spend a few minutes on the historical developments of the subject. So, the historical development of the subject of statistical inference we can attribute towards the first half of the 18th century, and mostly in the problems of astronomy and geodesy. So, in astronomy the interest was to find out the interplanetary distances, the positions of the various planets or stars and their movements. In geodesy one wanted to find out the spherical shape of the earth. So, it was known that actually the earth shape is spherical, but it is flat on the near the poles. So, a standard technique is to take observations, not one but several measurements are taken. For example, they are taken about the length of 1 degree of a certain meridian, and the problem is to determine parameters alpha and beta which specified the spheroid of the earth. So, indirect observations on alpha beta are given by the relation y I is equal to alpha plus beta x I. So, here x i's are given to us, y is given to us. So, alpha and beta are to be estimated. So, nowadays we understand this as a problem of simple linear regression. However, this problem was studied as early as in 18th century by Gauss and Legendre, who came up with the method of least squares to solve this problem. Even before Gauss and Legendre, about 50 years before that, Boskowitz in 1757, he proposed a solution for this problem, where he sought to minimize summation of modulus y I minus alpha minus beta x I. So, in place of the square, initially he considered the mean absolute error actually, subject to the condition that sum of the errors must be 0, and he solved this problem using geometrical methods based on 5 observations. Later on, Laplace has given a general algebraic solution to this problem. This can be considered as the first you can say attempt to solve an optimization problem under constraints. Later on, Gauss and Legendre considered the minimization of the sum of the squares, and that is why it came to be known as the method of least squares. So, you can consider the problem of statistical inference, or you can say the modern statistical inference started as early as in the 18th century. Further developments, or you can say the further techniques started to get developed towards latter half of the 19th century. For example, Francis Galton, he started to study something called the relationship between the variables, and he called it regression. So, he sort of predicted that the tall parents have tall children, but less tall than the parents, and shorter parents have short children in the height, but taller than the parents. So, this was called regression towards normality of the heights, and the first studies, or you can say first model of the simple linear regression were made in this time. Later on, Carl Pearson developed the method of moments in the latter part of 19th century. The modern methods of statistics as we know today, and probably they were first started by Fisher in 1912, where he developed the method of maximum likelihood. He is probably the first one when he realized the importance of comparing two different methods of estimation. So, he considered two estimates of the standard deviation. He found out the sampling distributions of that, and therefore, the mean squared errors, and he showed that one of the estimators has a smaller mean squared error than the other. So, probably this is the fundamental, or you can say path breaking paper in 1922, that is called the mathematical foundations of theoretical statistics, where he listed the basic problem of theoretical statistics as firstly the problem of specification, that is defining the distribution of the population. Second is the problem of estimation, and the third is the problems of distribution. That means, how to judge the goodness of the, or you can say evaluate the performance of the estimators, we need the sampling distributions of the statistic which are being used. So, these developments made by Fisher in 1920 to 40, and these had the effects in the various areas of statistics such as estimation, testing of hypothesis, designs of experiments. At the same time, Georgi Neyman and E. S. Pearson simultaneously developed a theory of testing of hypothesis. Neyman also developed the theory of sample surveys. Later on in 1940s, Abraham Wald developed a topic called statistical decision theory, and this includes various aspects of inference as special cases. He showed in fact that estimation, testing, ranking and selection procedures, they are all part of the general problem of decision theory, which is actually having its origin in the theory of games, which was developed in 1930s or 1920s by John von Neumann among others. So, friends, today we have discussed the basic problem of statistical inference, its main components. In this particular case, we will focus on the problem of estimation and testing of hypothesis. So, from the next class onwards, I will start discussion on the problem of point estimation.